Okay, so yeah, let's start our first seminar. So it's my pleasure to introduce yourself. So here we'll talk about the spectrum of singularity.
Yeah, so welcome. This is the first of two talks, and I will talk about the spectrum of a singularity. And this talk is meant to be introductory, so I will just say what it means. And so the plan is first the setup, so how we get the spectrum and from the singularities. Then I will show some basic examples of singularities and their spectra. Then I will talk about properties of singularities and their Milner vibration, monodromy, and something about the Hodge structures, which leads to the definition of the spectrum. And finally, I will discuss interesting properties of spectrum, which make them very suitable for applications. This will be Thom-Sebastiani theorem, semicontinuity, and Hertling theorem or conjecture. So let me start with saying that this spectrum was developed by Arnold, Varchenko, and then Steenbrink, and then by many others. So I will start with a spectrum of a hypersurface singularity, but it can be defined more generally. So, so the input is a polynomial in several variables. Such that all the partial derivatives at the origin. This is just to make it easy, and there are nowhere else near zero. Okay, so the polynomial has all the partial derivatives 0 at the origin at 0, 0, 0, and nowhere else in the neighborhood of 0. So we also say that when we have this situation, that f defines an isolated hypersurface singularity. So by isolated, we mean this property that the singularity is just at the point 0, 0, 0. Hypersurface means that we have one equation. So when we consider the equation f equals 0, we get a surface, hypersurface in Cn plus. So let me do like n plus 1 variables. And I also should say that the polynomial is over complex numbers, so it's going from Cn plus 1 to C. So it defines an isolated hypersurface singularity. Of course, I should know that the singularity can be defined by different equations. So this is up to by holomorphism. Can you read this green? Yes, okay. So up to biholomorphism, for example, you can have a like a polynomial x squared plus y squared, or you can have a polynomial x, y, and they define the same singularity because you can do substitution which changes one to another. Okay, and so this is the input, and now we have the output. which is the spectrum. So what is it? So it's a collection, finite collection of rational numbers. We call it here, I mean, now I call it spec F, which may be a little bit confusing, but this is the only spectrum which we will consider in this talk. So it's a collection of numbers A1, A2 up to A mu. And we can, I mean, kind of formally we can write that it lies in the group ring of Q, which just means that there can be multiplicities. Yeah, so the numbers can repeat. Yes, so those are rational numbers, and they have coefficient. They have integral coefficients. So formally, it's an element of the group ring of over rationals. So, but this is not really important for us. And so I will start with the examples so that you'll see some spectra before we get to the theory. Okay, so the simplest singularity, like this, is better, which defines an okay, so the simplest singularity is x to some power. Of course, n must be larger than 0. Then clearly we have the derivative at 0 is 0. And we say that it defines an singularity. So this is kind of the simplest singularity you can have. And the spectrum, so the spectrum, or maybe, I mean, let me write it here so that I can use this. So f is x to n plus 1, then the spectrum of this an is just 1 over n plus 1, 2 over n plus 1, up to n over n plus 1. So in particular, we see that this number mu, the number of elements, and this is what this n means here. Okay, so this is the first example. The second example is a surface singularity. So we have, this means that we have 3 variables, so they define a singular surface. So this is x squared plus y cubed plus z to 5. And so this is an, this is called a E8. And the spectrum of E8 is, let me write it like this. So 1, 7, 11, 13, 17, 19, 23, 29. And those are all fractions with common denominator 30. Okay, so I don't want to write it all over again. Another example, E12, for example, is a similar polynomial, just we put here 7. So now the spectrum gets a little bit longer because it has 12 elements, but I will write it down and try to keep it here. So -1, 5, 11, 13, 17, 19, 23, 25, 29, 31, 37, and 43 over 42. Okay, and the last example is T237. So this is a similar polynomial. but we add here some other term x, y, z with some coefficient lambda where lambda is non-zero. So it's actually like a one parameter family of the singularities, which are all non-isomorphic, but they have the same spectrum, which is one of the properties of the spectra, that they stay constant in families. So spectrum of T237 is 0, 6, 12, 14, 18. I hope you can read it here. 21, 24, 28, 30, 36, 42, and again divided by 42. Okay, so as a check, you can count that there are 12 elements here, and here we have 2, 4, 6, 8, 10, 11. So one less. Okay, so those are the examples. So we see that we start with the polynomial and we get some collection of rational numbers with a common denominator. So, okay, so now so those are the examples. So we are pretty fast. We are here. So let me erase something. Okay, so now I'll talk about the Milner fibration. Okay, so let's start with the picture. So we have this C to n plus 1, and there is C, and the polynomial is just a map from Cn plus 1 to C. So here is 0, and we know that the preimage is a singular surface or curve or hypersurface in general, and also that when we take some small number close to 0, then we get a nice smooth surface. Okay, so this is like f, the preimage of 0. This is the preimage of some t, where t is very, very, very small. Okay. In general, there can be like some other singularity very far away, but this is all local story. We only care about the neighborhood of 0. Okay. And what can we do? So we can intersect. So we can. So first of all, we take this like small neighborhood of 0, and we can also intersect. So I'll draw it like a ball with a neighborhood of, so some b delta. Oh, so let's say the epsilon. We have t is smaller than some delta. So we intersect with a ball in Cn plus 1, and if everything, all these like parameters are small enough, then we have the following thing. So we call MF this smooth intersected with this. Now it's the 2n plus 2 real ball, and so we call this Milner fiber. And so the purpose. So first of all, it's a smooth. It is a smooth manifold, right? Smooth 2n manifold, because this lowers the dimension by 2, and So this is the first thing. The boundary of MF is also interesting for us, and it's we call it LF. And so this is the intersection of smooth fiber with the small sphere. Yeah, so we take a small sphere around 0 and we intersect it with the smooth fiber. We call this so this is Milner fiber, and we call this link of singularity. Yeah, probably you may see like for the definition of the link you mostly see like that we take the singular fiber and we intersect it with the small sphere. But in case of the isolated singularity, those two are homotopy equivalent. So for our purposes, it's the same thing. But in general, if the singularity is not isolated, this is the link of singularity, and this can have some interesting properties, and it's more complicated. But here, it's kind of interesting and important that this is the same thing for us. So this is the link of singularity, and it is also a smooth manifold. Here we have like a singular thing, but we ignore the singular point. We take sphere, which doesn't go through the singular point. So this is 2n-1 smooth manifold. Yeah, and so the most important thing is that this like, so okay, so this MF, this MF depends on this parameter T, and it defines a smooth vibration, like trivial, smooth, locally trivial. Vibration over this B epsilon of 0 inside C without 0. So it means that Z is like here, and we have these different fibers here. And this is all like a smooth vibration. There are other fibers. And this has an important consequence that we can go around 0, make a loop, and we get a map from the fiber to itself. And this is called geometric monodromy. And if we take just what it gives us on the cohomology of the fiber, we get the usual monodromy map. So yeah, so this is the fourth property is that in case of isolate, yes? Is it so this is like a disk in C. I just wrote it like because like ball in C is disk, right? Yeah, sorry, this is like maybe I messed up. Yeah, so there is a delta here. Yeah, sorry. Yeah. Okay, so yeah, so the important thing is that the cohomology of the Milner fiber is actually just the middle cohomology, because all other are trivial, and except the zeroth. But yeah, so the only interesting part is this middle cohomology, because the fiber is actually homotopy equivalent just to bucket of spheres. And we have this, so the last thing, we have this 5 monodromy map. Which we call T, and it goes from Hn of MF to Hn of MF. And this will be very interesting for us. So this is given by the parallel transport along this loop around zero, around the singular fiber. Okay, so maybe let's do some more example. Okay, so if we take fx p plus yq, then just to see what is the link, so the link of the singularity. So we have two variables, so it means that n is 1. So it gives us one manifold, which is embedded in this sphere because we intersect with this 3 sphere. So it's a one manifold inside S3, and one manifold inside S3 is a knot, right, or link. So yeah, it's a little bit so it might be a little bit confusing that we call this link, and there are also links which mean like that we take bunch of nodes in S3, but so this is also called link, unfortunately. So we get, so for example, if we take this xp to yq, and if suppose that they are coprime, then we get LF is this PQ torus knot. Or if they are not coprime, we get PQ torus link. So we get more components. Okay, so this is an example of the link of singularity. And maybe it's like for the monodrome, so if we take this AN singularity, then we can draw it like this. So here we have 0 at C, and we have, so here is C, here is another C, because this is just x to n plus 1. Okay, so pretty much the singular point is 0 with like multiplicity n or n plus 1, and they're like, so this is, let's use another color. So this is the smooth fiber, yeah, because if we take slightly different point here, then the pre-image in n plus 1 is just like n plus 1 points. So the monodrome goes like this. It changes the roots of unity in this like cyclical fashion. So if you have like a generator for each of these dots, and you get a matrix. Okay. So yeah, those elements of there is like a kind of like canonical basis of this cohomology, which is given by the vanishing cycles, which are the cycles which disappear when you go to the singular point. So let me do one more example of a link. So F is x squared plus y. So in this case, this is a 3 manifold inside S5, and there is a big difference between this like curve case and singular surface case, because here we just have like one manifold, and one manifolds are pretty boring. They are just circles, and the interesting thing is the embedding into S3. But here we get a non-trivial 3 manifold, which is different than S3. And it's not really clear, or at least to me, it's not really clear what is the meaning of this embedding. Yeah, there are papers of Borotik and Nemeti which try to study this embedding and define Alexander polynomial, kind of do like a knot theory in higher dimensions. But apparently there is like a mistake in the paper, so like the basic things in knot theory fail in this case. So it's not really clear how to work with these embeddings. So, but we still have this 3 manifold, which is pretty interesting, and we can ask, this is an important question, very odd question, how much of the properties of the singularity is hidden just in the properties in the invariance of this three manifold. So what is this three manifold? It's a very famous one. It's so-called Poincaré homology sphere. Poincaré homology sphere, which we write like this, because we have 2, 3, 5 here. So what is this? So it's a three manifold, and it looks like a sphere. It's not. So what do I mean with the statement that it looks like a sphere? So if you look at the cohomology 2, 3, 5 with integral coefficients, then it's isomorphic, or it's the same basically as the cohomology of three sphere. So when we have such a three manifold, we call it homology sphere. Okay, so if the homology of or cohomology of a three manifold is the same as the cohomology of three sphere, then we call this three manifold a homology sphere. It will be also important for us the case when just the rational cohomology is the same, then we call it Q homology sphere. And this means that there can be some different, some non-trivial torsion in the cohomology. Okay, so in this case, this holds even for Z. But for example, if we take if we take 2, 3, 4, so there would be like x squared plus y cubed plus z4, then we would get some non-trivial torsion. So this is kind of special property of this. So the point is that these three numbers are pairwise coprime, which gives us this property. So it's a homology sphere, but it's not a sphere, because if we look at the pi1, the fundamental group that we can compute, that it has 120 elements. It's a double cover of this like symmetries of this iso like this Platonic solid, which I cannot say. Okay, so so this is an interesting three manifold which comes from the singularity theory. And maybe last thing is that it's really important that we have we take a small epsilon here, because when we write and we make it really big, we can get a link over different singularities. So this happens with this E12 and T237, that if you change the epsilon, then you jump from one to another. Okay. Yeah. So this is the Milner vibration, and now we want to get back to spectrum. So okay, so this cohomology, which is like some vector space. So we know that it has this, there is this map T, which goes from H, and it's an automorphism. And but there is more structure in this vector space, and it's a mixed Hodge structure. Yeah, I don't want to get much into this, but important thing for us that there is a like a decreasing filtration F on this HN. There is also this weight filtration, but we don't need it for spectrum. So let me do some so I mean, I won't define this mixed structure. It's pretty complicated, and this was done by Steenbrink in his papers. So it's, I mean, it's really complicated. I cannot say that I understand it. I should, but yeah, for us, it's a fact that that we have this mixed host structure on this vector space. So suppose that we have this situation. So we have a vector space V, an automorphism. So V, V is a vector space. T is a finite order automorphism, and we have a filtration of V such that T preserves F. Then so we can then we can split the VF as a sum of eigenspaces of this T. So we have this VAF, where A goes from -1 to 0, and VA is kernel of T minus e to the minus 2 pi I A. So so this T is finite order, so it means that these eigenvalues are roots of unity. So we take various roots of unity and we split this V, including this filtration, into eigenspaces of these roots of unity of T. And now, so we have this monodromy, which splits the vector space into eigenspaces of roots of unity, and the spectrum are rational numbers. So they're like logarithms of roots of unity, right? By this e to the 2 pi I. So we want to use this filtration to get kind of like these logarithms, or the proper logarithms of these roots of unity. So the spectrum of VTF n, which is just like we have Hn, is a sum over all A and sum over all P. So A goes through these numbers between -1 and 0, and P is the index of the filtration of dimension of the graded piece of the filtration F of the eigenspace, and then we take the number np plus a, and this all lives in the group ring. So okay, so this is like this. This is like this integer which we take. The rational number, because this is a rational number. This is just like a global shift by the dimension, and this is the shift by the index of the filtration. So like the index of the filtration tells us which preimage in e to 2 pi I we take of the eigenvalue of the monodromy. Okay, and the dimension of this graded piece tells us how many, because we can have these multiplicities. So yeah, so once we have this mixed structure, so I mean, the monodromy doesn't have to have finite order. So we take the semi-simple part, and then also the monodromy doesn't have to preserve the Hodge filtration. But if we take a semi-simple part, then it preserves the Hodge filtration, so we can use this definition and define the spectrum. So maybe it's good just to draw like a picture to make it clear. So like in case of surface, Okay, so we have like fx, y, z. And the spectrum in one, which is in use, lies between -1 and 2. And we have this 2 pi I, which is sending it to the unit circle. So we have like some eigenvalues of monodromy. They can look like this. So there can be like 1 and -1, and this and this and this and this. Say, so it means that this is like the information which is given by the monodromy. It's eigenvalues, and we can like, for example, for this, the preimage can be this or it can be this. So there is a choice given by this filtration. Yeah. And we have this third. So it can be here, it can be here, but it can also be like here. Yeah, and maybe like this. So the spectrum can look like this. Yeah, and it's really interesting that it kind of goes out of the interval 0, 1. So now we can look at the examples again, and we can see that, for example, this first one and the second one, the whole, so those are all, I mean, we can make the AN singularity. So the AN singularity, we can make it surface singularity if we add 2 variables just like this. So this is called like stabilization. If you just add second powers, then nothing really happens. I mean, it depends on the way how we define the spectrum, like about the global shift, but so it can shift the spectrum by 1/2. So the spectrum lies in the interval 0, 1. And no, there are no elements outside of it. The same for E8, but here you can see that there is this -1 over 42 and 43 over 42, which are outside of this interval. So there is this classification, like the classification of the simplest singularity. So there is this ADE list, which is so those are the simpler singularities. So it means that they have no moduli. There is no parameter like this. And they are classified by Dynkin diagrams, AD Dynkin diagrams. And those are exactly the hypersurface singularities, which have this property that the spectrum is in the interval 0, 1. Okay, so the spectrum kind of gives us a different characterization of ADE singularities. And then we have some more interesting singularities like this E12, and it goes out. Yeah. So this is like so many invariants of the spectrum can be computed. Sorry, many invariants of the singularity, like more classical ones, can be computed from the singularity. For example, this PG, like the geometric genus, if I'm not mistaken. So it's a number of elements of the spectrum in this interval -1, 0, like for a surface. So it's exactly the number of the elements which are outside of this interval 0, 1. And I mean, maybe the most classical invariant is this Milner number, which I call mu, and this is just the number of the elements of the spectrum. So this is just the rank of this vector space. Yeah, and maybe like some more interesting example. So if we take this, so let me erase this. So this Poincare homology sphere is a special case of a family of singularities which are of type xp plus yq plus c r, where pq are coprime, pairwise coprime, pairwise coprime. So this is called. So this is an example. This is called a Brice-Korn type singularity. So the link is again a homologous sphere. And we can, so when we have a homologous sphere, there is this famous Casson invariant. So this Casson invariant of this link LPQR. So I mean, it's related to the signature of the Milner fiber. I'm sorry, but I'm not completely sure about this 1.8, but maybe there is like a minus or something. But there is like a real, so this is like a 3-manifold invariant, which is related to a 4-manifold invariant, which is the Milner fiber. And we can get this by computing like, so I mean, it's related, so the signature is related to this PG and mu. And we get it by like taking T0 minus T1 plus T2. Also, I guess there should be this 1.8. And this is like the number of the elements of the spectrum in this interval minus this interval. Yeah. I mean, I had these lectures in Sofia, and then I lost my notes, so I was doing them again, and I might not remember something correctly. So if you remember, then please correct me. But the idea is like this, yeah. So this is kind of interesting because it tells us that the Casson invariant is like enhancement. You know, it is just one number, yeah. And now we have like a bunch of numbers, and they all are interesting. So why are they interesting? So now we are coming to the properties. Okay, so. So this is when where it gets really interesting, because it would be boring if we just have like a collection of numbers and there are no interesting properties, but there are very interesting properties. So first off, the spectrum of f is in the interval -1n, f going from Cn plus 1 to C, so for n plus 1 variables. And moreover, it's symmetric around this like middle point of this interval. So this is one interesting property. It's the symmetry. The other one, sorry, where is m? There is only n. This is around. I'm just like saying that this is symmetric by around this point. Yeah, so it's like the spectrum. Whenever you have a point here, you have also a point here and here. Okay. So the second is famous Thom-Sebastiani theorem. Which tells us that if we take f plus g and we take the spectrum, then it's a spectrum of f plus spectrum of g. And I have to explain what are these, what this means. So this is like a Thom-Sebastiani sum of two polynomials, which just means that we take a polynomial in variables x1 up to xn, and then we add like a different polynomial in different variables. So they are completely independent variables. Yeah, so we can take two polynomials and add them up, and we can ask what is the spectrum, and the answer is really nice. So it's this sum of the spectra, which means that we take every element of the spectrum of f and we add it with every element of spectrum of g. So we get like a long list of numbers. There is like a different notation. this is the, I mean, this is like a F plus, like this O plus in like a, this is the mean, yeah, this is the summation, yeah. I mean, it's kind of confusing to write just plus, yeah, but I mean, it's basically it is the point is that the variables are different, okay? And so this, so we can see this here and here, yeah, because those are actually just like this E8 in terms of this Thom-Sebastianism is like this E1 plus E2 plus E4, and this is just plus E6. So you can easily compute and try that if you take this for like E1, E2, E4, and you add them up, then you get this and this. It's like an exercise. And so this is the Thom-Sebastiani, and the maybe the most interesting is the semicontinuity property. Okay, so I said that the family there are like families of the singularities, like this one, which have the constant Milner number, and you can also prove that they also have like a constant spectrum, but then they can suddenly jump to a different family, which is like this is also a family that you can add some other term like 5, I mean of degree 5 or something, but you see that if you put lambda here 0, then you jump from this family to this one. So the Milner number jumps because here it's 11 and here it's 12. And this means that the spectrum also jumps. And we call this adjacency. So if we have like this, that this T237 is adjacent to E12. Oh, sorry, the other way. So T237, yeah, E12. So the picture is like that we have this T237 family for lambda non-zero, and then suddenly there is this like a different family for lambda 0, but there is some other parameter mu, which I don't write here, and there is this E12 family. So it means that this T237 family kind of touches this one, okay? And so the semicontinuity theorem of Varchenko and Steenbrink says, and it's originally a conjecture of Arnold, says that the spectrum is kind of semi-continuous with respect to these adjacencies. So this is called adjacency. So in general, this is like a very open problem to find out whether there are adjacency between different types of singularities. It's hard to prove that they are not. And the spectrum is one powerful tool how to prove that there is no adjacency. So the semi-continuity theorem, maybe I can, let me erase this. I'll do it here. So it states this. So if we have this F and there is a adjacency of G, then for any like this type of unit interval, we have this. So the number of elements of spectrum of F intersected with this interval is less or equal the number of the spectrum in the same interval of G. So you can go and really check that this works. Yeah, that if you take any interval and you count the numbers in the interval, then it's less for T237 than for E12, which is really interesting. And it has like some like easy consequences which are easier to check and they're not so strong. So for example, it means that the least number in spec F is greater or equal than in spec of G. Yeah, because there are more numbers in E12, so you can like take the interval, which is just has this one number in it, and it's so close to the number that there can be no numbers in the other spectrum. So you can just look at the least numbers. The other is, for example, that the PG of F is less or equal PG of G. The other one is mu F mu G. Yeah, and there are many other invariants which have this semicontinuity property, but for example, for those, it follows from the semicontinuity of spectrum. Recently, I learned from a paper of Borodzik and Livingston, and also another paper, that there are some other invariants which have this semicontinuity property, like this semi-group of a singularity. So this is like a common topic in this subject, to try to find things which behave in this way. And spectrum is famously one of them. Okay, so
Joseph?
yeah, we have. I think there is a question.
Yeah. So Joseph, so for your properties of the spectrum, your first property seems to be following the Steenbrink formulation.
Yeah.
But your second property is following the Saito formulation.
I'm sorry. Yeah, you're right. So you're right. So yeah, this is like kind of a bad thing. So so there are like two different ways how to have the spectrum. So one is in the intervals -1 and 0. This is used in the most of papers, like the Steenbrink's papers. And the other one is like in the interval 0 and n+1. And this is nice because then the Thom-Sebastiani theorem works like I wrote it. Yeah? If not, then you have to like subtract 1 or something, yeah, because you always like shift it to the interval 0 and +1, then it works like this, and then you have to shift it back to -1. And so thank you for this. Yeah. Otherwise the theorem wouldn't be true. So yeah,
I think it's
yeah, something like this. Yeah, it's really about like the global shift of the spectrum, which is not really important, but yeah, it's important to have one convention. Okay, so I think I'm basically out of time. There is like a fourth interesting thing which I want to talk about. It's this Hertling conjecture. So this tells us that if we take like variance of these numbers, they're actually related to the difference of the least and largest number. In large class of singularities, it's inequality by Hertling, the theorem, and in general, it is just a conjecture. So this also tells us that there is some interesting kind of like a global structure in the spectrum. Yeah, and so I wanted to talk about like, okay, so do you have, how much time can I have? Like 5 minutes, okay. So this Hertling conjecture, let me just write it. So I'll put it here, okay? So it says that if we take 1/mu, the number of elements of the spectrum, and here we take like we take the variance. So we take like a difference from the mean value squared over elements of the spectrum, then it's less or equal a mu or minus a1 over 12, where a1 is the least number. So this is a really interesting conjecture which was proved for so-called quasi-homogeneous. So it's theorem for quasi-homogeneous singularities. Quasi-homogeneous means that we can give to each variable a weight such that it can be a rational number, such that together the whole polynomial has like a one degree. So for example, these three are quasi-homogeneous and this one not, because you cannot give like weights so that the degrees of all these terms are the same. So it's a theorem for, and it's actually an equality for this. Yeah. So so the last thing I want to say is that there are many applications. So I'll just mention them. So first of all, there is this so applications. First of all, there is this adjacency problem. Okay, so spectrum gives us many like statements, theorems that some adjacency is not possible. Okay, so this is so far everything was local. We were just treating like little neighborhoods of some singular points, but surprisingly, spectrum also have like a global application. So it gives us a bound on a number of singular points. Of a given type. On a global hypersurface. In Pn. Okay, so I mean, this is like a trick which gives us that we can kind of add up the spectrum, and it gives us so we can ask like how many A2 singularities can be on a degree 5 hypersurface, yeah, and this gives us some bound. So this is very interesting, and so there is this like possible application to birational geometry. Which relies on like some conjectures and like so there is this idea that spectrum should be coming from the stability conditions on a category, but I think like many people will talk about this later. So these are some applications, and so I promise that I will talk about the computation. So there is this program Singular. So just that you know, which can compute the spectrum of a hypersurface with this library spectrum .lib or GMS sync. So I mean, it's good to have in mind that there is like a computer program which you can use, but it's not really. I mean, the problem is that the spectrum was defined more generally, so not just for a hypersurface, but for intersection of hypersurface. So for like isolated, complete intersection, and there is no library for this. So this is kind of so the most important message of this talk is that like if somebody would be willing to make a program, a code to do this isolated complete intersections, I think it would be very good. I'm just so bad in code, so I haven't succeeded yet. But if somebody wants to do it, then I think it would be very, very useful. Of course, there are some computations by Steenbrink, but in general, I haven't seen anything. Okay, so I think it's all.
Okay, so yeah, that's thanks to Josef. So is there any question? So there's a question like, so is the spectrum of complete invariant of an isolated hypersurface singularity?
Oh, it's not. So there is some like, yeah, I mean, for example, there are these, so I said that we kind of ignore the other filtration of the Hodge structure. So if you don't ignore it, you get these spectral pairs, which is slightly more information. And there are some other things. So So in general, it is not, but it's a pretty strong invariant. Yeah, but yeah, there is this. Yeah.
If not, how complicated is the counterexample?
How complicated is a counterexample? I think it's not very complicated, but from the top of my head, I don't think I can give it to you. But it's definitely in the Steenbrink's papers. You can, or I mean, the good source for this is also the Arnold and others book on singularity theory, and also the good source is this Arnold et al. I think it's the volume 2 of singularity theory. Theory volume 2, or also the Steenbrink and somebody, sorry, I forgot, I don't remember. So the book on mixed structures, they have a, and I think there is also another book you wanted to use for the seminar, right? This Kulikov, yeah. So yeah, so you can find the counterexamples. Yeah. It also has something to do with like the fact that these matrices, so we kind of only use the eigenvalues, right? But the monodrome matrix is like an integral matrix on an integral cohomology. So there is distortion, yeah, and some like integral information.
Okay, is there any other question? Okay, that's not. That's thanks to Josef again for we will